Hi, in this lecture we will be talking about correlation, and I'm sure this is a topic that many of you have heard about before. Perhaps the phrase correlation does not equal causation. That is a commonly referred to phrase in statistics, and in this lecture hopefully you'll learn why. So first, the definition of a correlation is that it describes the relationship between two numeric variables. And if we're being very technical, it's a number that describes the relationship between two equal interval numeric variables. So for example, we could look at the relationship between high school GPA and college GPA. And again, just using your statistics gut, your statistics intuition, you might think, people with high GPAs in high school are likely to have high GPAs in college. That means those two variables are correlated. Or we could think about a correlation between SAT scores and college GPA. Presumably, those variables should be related. Or hours spent studying, we hope, is related to the exam score. So the number of hours someone spent studying is a numeric variable, and then their exam score is another numeric variable on two different scales, but we can still assess how those two different variables are related to one another. In this lecture, I'm going to break correlations down into 4 sections. So I'll start with how to graph correlations or how to visualize correlations, and then we'll ease into patterns of different correlations. So we graph them to look at the patterns. We can talk about several different patterns that correlations could take. And then we'll talk about how to actually calculate the correlation and determine statistical significance. And finally, we'll talk about how to interpret correlation and how not to interpret correlations. Often the best way to describe a relationship between two variables is to right away draw a scatter plot of the data. Often the very best way to start thinking about or describing the relationship between two variables is to visualize the data on a scatter plot. So we could create a scatter plot, for example, for marital satisfaction scores and another numeric variable that represents the number of exciting activities individuals report that they engage with their partner in an average week. So the two numeric variables are the marital satisfaction score and the number of exciting activities reported. And you can see if we have the number of exciting activities down on the x-axis of this scatter plot on the screen, and then we have marital satisfaction on the y-axis or the vertical axis. And just looking at this, I want you to think about what you notice, just looking at the scatter plot. One thing that hopefully you're noticing is that there tends to be a relationship here. There tends to be a pattern. And I know you haven't learned about it yet, but just intuitively you can see that there are people who have lower general marital satisfaction scores, so who are on this lower end of the y-axis, also tend to be in the lower end of number of exciting activities with a partner. And then people who are on the higher end of marital satisfaction tend to have more exciting activities with their partners. So you can see that there tends to be a relationship here. And you can see how important visualizing the relationship between two variables can be and how much information it can give us right away. So let's walk through the steps for making a scatter plot, or sometimes called a scatter diagram. And the very first thing you want to do is draw your axes. So you're drawing an x-axis and a y-axis and assign variables to them. It doesn't really matter most often which variable goes along which axis. Every once in a while there's something that might be more intuitive to you to put along one of those axes, but it really doesn't make a difference at all. Then you want to determine the range of values for each variable. So the possible range of values for each variable should be expressed along their respective axis. You want to make sure that the axis spans the full range of possible values for each axis, the x and the y. And then finally, you're going to put a dot on the graphing plane that represents each individual's pair of scores. So let's look at an example. And this is a different example so that we can create our own scatter plot. And this is also from the book. It's an example of data from 6 individuals. And we have information on the number of hours that the individual slept and their mood for the day. So how many hours did they sleep the night before and what is their mood today? So the very first thing that we do is we create our y-axis and our x-axis. I'm going to put hours slept on my x-axis and I'll put happy mood on my y-axis. I'm just using shorthand right now. Alrighty, so I want to now figure out what range of values I should put along each axis. So for number of hours slept, it looks like the lowest score here is 5 and the highest is 10. But I'm going to go ahead and I think possibly someone could have slept 0 hours. So I'll go from 0 to 10. Let's put 5 in the middle so we have that as a reference point. And then also I need to figure out the range for the mood variable. And you can see that these scores for happy mood range from 2 to, I see a 7 here as the highest score. So let's say we're going to go up to 10 as well. We'll keep things consistent. So 0, 5, 10 on the x-axis and 0, 5, 10 on the y-axis. And then finally, we need to figure out each individual's pair of scores and then put a point on the plot for each individual. So for person 1, I could express person 1's pair of scores, or otherwise known as coordinates, on a plot, right? Maybe that sounds familiar from a previous math class you've taken. So we can see here that person 1 has an x score of 5 and a y score of 2. And you could express that the way I just wrote it, in parentheses 5, 2. And we could do this for everybody here. Once you have your coordinates for each person, then you can go ahead and plot them on the plot space. So I won't do them all right now, but you can see that for the first person, we have an x score of 5. So I'm going to find along my x-axis, remember that's hours slept, I'm going to find the point 5, right, which is right here. So 5, and then on the y variable, happy mood, they have a value of 2. So that's maybe like right here. So I'm going to put a point that represents that individual's pair of scores. I could also do a point for the second person who slept 7 hours and has a mood of 4. So 7 hours, somewhere on here, mood of 4. I'm going to put their point right there. Okay, so I'm going to stop here, but you might want to pause the video and practice making a scatter plot with the rest of these points. Okay, because I have the full scatter plot on the next slide. So hopefully, if you did make your own scatter plot with the data on the previous slide, you ended up with something that looks like this. We're typically graphing correlations so that we can identify some sort of pattern in the relationship. And there are 3 types of patterns we could identify by looking at the scatter plot. We could identify a linear pattern, a curvilinear pattern, or a pattern that suggests there's no correlation, which is essentially no pattern at all to detect. So let's look at those different patterns. A linear pattern or a linear correlation is a pattern that you could draw a straight line through, and that straight line would generally describe the points on the plot. So the points don't have to literally align in a perfect straight line, but they should generally fall along a straight line for you to conclude that there's a linear correlation. Linear correlations can be either positive or negative. A positive linear correlation is one where high scores on one variable go with high scores on the other variable. And then low scores on one variable accompany low scores on the other variable. And if you think about this visually, it means that the line will start low and end up high. So the example that we just worked through together for our scatter plot, happy mood and number of hours slept. Low scores on hours slept correspond to low scores on the mood scale, and high scores on hours slept correspond to high scores on the mood scale. So if you drew a line through the points on our scatter plot, you end up with starting low, and then you have like a line that goes up, or in other words, it has a positive slope, indicating that there's a positive correlation between these two variables. We could also consider a negative correlation, and that's a correlation in which high scores with one variable go with low scores or opposite scores on the other variable. Low scores on one variable go with high scores on the other. And visually, in a negative correlation, a negative linear relationship, the line that you draw in your scatter plot through your points will start high and end up low. And the example that I have here is marital satisfaction scores paired with boredom in your relationship scores. So people who are really bored, so they have really high scores on boredom, have low marital satisfaction. You can say here, people with really high scores on boredom have generally low marital satisfaction scores. So that is a negative relationship. Notice it's still linear because I can draw a line through the points on the scatter plot, and it looks like the line pretty well describes the shape of the points, or the shape of the cluster of the points. Unlike the pattern in a curvilinear relationship. A curvilinear correlation has a pattern of dots that's actually curved, just like the name would suggest. So this example here that I have for you, also from the textbook, is an example from a memory task where participants are given a word list and then asked to recall the words on the list. And you can see on this scatter plot that I have, you can imagine points surrounding this line. The points are just left out of this plot here. You only see the line. But this line is drawn to fit through points on a scatter plot. And you can see that there are people who do pretty well remembering words at the beginning of a list. And they also do pretty well remembering words at the end of the list, but they don't do very well recalling the words in the middle of the list. So not as many people remembered words in the middle of the list. So if you drew a line through the scatter plot or through the points on this scatter plot, you would have a curved line. And it's because people are not remembering words in the middle, but they're remembering words at the beginning and the end. And that, if you have taken a course in cognition or learning, or maybe just intro to psych, you might remember is because of what we call the recency effect and the primacy effect. People are more likely to remember words at the beginning of a list due to the primacy effect. They're also more likely to remember words at the end of a list due to what we call the recency effect. So this is an example of a relationship that is curvilinear because you couldn't draw a straight line through the points to describe the relationship. Instead, you would draw a curved line through the points. And finally, if you plot the relationship between two corresponding variables and you see no particular pattern, then we would say that's indicative of no correlation at all. So this is the case for when two variables are not related. The example here is income and shoe size. This is from the book. I'm sure there's, one could argue that there actually could be a relationship between these two variables, unfortunately. But in this case, we see data that shows no particular pattern. I could draw a line here, I could draw a line here, I could draw a line here. Any one of those lines is equally descriptive of the relationship or not very descriptive of the relationship, right? So there's no obvious trend here. So I say that it doesn't look like there's any correlation at all. Another useful way to describe correlations is to discuss the magnitude or strength of the relationship. So you can see here that a stronger relationship has points that fall closer to the line that one would draw through the points. So the closer those points are to the line that you would draw through those points, the stronger the relationship between the variables. The more spread out the points are, or the less obvious the pattern, that means there's a weaker relationship. So it's kind of intuitive, right? The more clear the pattern is, if it really pops out and it's very obvious to you, it's probably a strong relationship. If you have to look at the image for a little bit to determine what the relationship is, then it's probably a weaker relationship. And you can see here there's just 4 examples of a variety of magnitudes of relationships and positive and negative correlations. On this slide, I have a summary of different correlation types. We discussed that relationships can be linear, curvilinear, or non-existent or no correlation. And then that linear relationships can be further broken down into positive and negative linear relationships. Let's move on to calculating the correlation coefficient and determining the significance level of a relationship. So the goal of correlational research is to describe the relationship between 2 variables. So we want to be able to determine how strong the relationship is and the direction of the relationship. And typically what we're calculating are linear correlations here. So you want to determine by scatter plotting the data that there is a linear relationship. If there is a linear relationship, then you can go ahead and calculate a Pearson's correlation coefficient, or Pearson's R. And the Pearson's correlation coefficient will tell us how strong the relationship is, or the magnitude of the relationship, as well as the direction of the relationship. And to calculate Pearson's R, we're going to use a variation of something that you've seen before, a z-score. So this is the formula for Pearson's R, denoted by a lowercase r. And remember, this here means the sum of, and what we're summing is zx times zy for each person, called a cross product. The product of a z-score for x and a z-score for y for each person. And then you divide by n, or the number of individuals. Another example from the book is job success and a test score. You could see that we would first visualize the relationship to make sure that it's linear. And this looks approximately linear to me, right? We could draw a straight line that pretty adequately describes the relationship between these 2 variables. So I'm convinced that we're safe to go ahead and calculate Pearson's correlation coefficient. So step 1 of calculating the correlation coefficient is to calculate a z-score for each participant for each variable. So we end up with 2 z-scores per person. And remember, we have to think back to what a z-score is, that a z-score tells us whether a person falls above or below the sample mean. So positive z-score means that they scored above average for the sample, and a negative z-score would be for someone who scored below average for their sample. And also remember, it's in units of standard deviations. So someone who has a z-score of positive 2 has a score that's exactly 2 standard deviations above average. Someone with a z-score of negative 1.5 has a score that is 1.5 standard deviations below average. So recall that from the z-score unit. And you have a reminder of the z-score formula on this slide. Z equals x, or an individual's score, minus m, which is the sample mean, over SD, which is the sample's standard deviation. And remember, we can calculate standard deviation as the square root of sum of squares divided by sample size. So once you've calculated a z-score for each variable x and y for every individual, the next step is to calculate a cross product for each person. So you're multiplying their two z-scores together to get zx times zy for each person to get their cross product. After you have a cross product for each person, then you add those all up. And that gives us the sum of zx times zy, which you might recognize as the numerator of the Pearson correlation coefficient formula. Okay. And then finally, we divide by the number of people to derive the average cross product. And then the average of all the cross products is also known as Pearson's R. So that's actually how we calculate a correlation coefficient. We calculate the average cross product for the sample, and that is the same thing as Pearson's R. So on this slide, I just have a summary of those 4 steps, all on a single slide. I just want to make some notes here about the convenient properties of this formula. First of all, the formula uses z-scores, which are standardized. So that's why we're able to compare variables or look at the relationship between two variables that are on different scales. Because in the computation of Pearson's R, we standardize both variables so they are on the same scale of standard deviations. Remember, that's the definition of a z-score. And then we can look at the relationship between the variables. Also, Pearson's R will always result in a positive number for positive correlations. So that's convenient because we can look at the value of Pearson's R and automatically we know if there is a positive relationship or a negative relationship. And also, finally, the result of Pearson's R will be exactly equal to 0 if there's no correlation. Another thing here, another note here is that Pearson's R ranges from -1 to +1. So the value of Pearson's R also tells us something about the magnitude of the relationship. The closer the value is to -1 or +1, or the further away from 0, the stronger the relationship. The closer to 0, the weaker the relationship. And as I just mentioned, if the correlation coefficient is exactly equal to 0, it means that there is absolutely no relationship between the two variables. And this is just a table that shows us how that works. If you are someone who wants to get into understanding how the formula works or how Pearson's correlation coefficient works like such magic, right? And you can think about it this way. The cross product of the z-scores will be positive if both z-scores are positive or if both z-scores are negative. So for each person, if they have a high score and a high score, they get a positive cross product. Right? And if they have a low score on X and a low score on Y, they also have a positive cross product because a negative times a negative is a positive. But if people who are high on X have low scores on Y or vice versa, then we end up with a negative cross product because we're multiplying a negative value by a positive value. And if someone has a 0 z-score or they score on average for either one of the variables, then we end up with a cross product that's also equal to 0. Okay, so now that we've learned about the Pearson correlation coefficient, and don't worry, I'll have an example for you later, we still might want to know if the correlation is statistically significant. So we calculate the value of Pearson's R, but if we want to know if Pearson's R is statistically significant, then we can use a t-statistic. And this is the same t-statistic that you've learned about. This is a different way to calculate it, but it will fall in the same distribution. So t can be calculated using just values of r that you've already calculated, and we also need to know sample size to calculate this t-statistic. Just for clarification, this is a number 1 here. Okay. So if you plug those values into this formula here, you'll get a t-statistic, and you could look up the critical cutoff score you'll get a t-statistic that falls on the t-distribution, and you could compare that to a critical cutoff value that you find in the t-table using degrees of freedom equal n-2 for a correlation test. So how do you interpret the correlation coefficient? Well, remember that a Pearson correlation coefficient can range from -1 to +1. And a value that's -1 describes a perfect negative correlation. A value of +1 describes a perfect positive correlation. And a value of 0 suggests that there's no relation between the variables or no correlation. So we can detect if there's a strong relationship or a weak relationship and whether it's positive or negative. But what we cannot do is determine that one variable causes the other. And there's a reason for that. It's because we don't know which direction the relationship goes, or in which direction it's working. So if you think of the example of number of exciting activities and marital satisfaction, just because we see a relationship between those two variables, it doesn't tell us in which direction the relationship is working. So it's plausible to think, for example, that couples who engage in many exciting activities together, therefore, are happier in their marriages. However, it could also be the case that marital satisfaction is causing the exciting activities, right? If you're happier with your partner, then you may be more likely to want to spend a lot of time with them. Or maybe neither one of these variables is the cause of the other, but there's one single variable that's causing both of the variables we're witnessing to change in the same direction. So there's an invisible variable that we are unaware of in our study that is working in such a way that we are seeing a relation between our variables. So for example, this variable, we'll call it Z, a Z variable, could be low work stress in this example. So people who are not that stressed at work have higher marital satisfaction, and also people who are not that stressed at work will have more time to engage in exciting activities with their partner. So in this case, it's the work stress level that's causing both of our observed variables. And because we can never know which one of these is true, which is the correct story about the relationship between the variables, we can't say anything about causation. And that is the end of this lecture. In another lecture, I'll walk through an example of how to calculate a Pearson correlation coefficient and how to determine if it's statistically significant.